Okay, this is going to be a video walkthrough of the hashing question. I believe it's question 5 on Spring 21 Midterm 2 in CS61B. Let's jump into it. Part A says, throughout this problem, assume we're using a hash table as seen in lecture to represent a set. Suppose that each bucket of the hash table is stored as a left-leaning red-black tree, and we are inserting items that implement the comparable interface. Which of the following statements are true about such a hash table? And so just to kind of get like a mental idea of what's going on, we can draw out our hash table, right? It's like an array with some, we're going to say M number of buckets, and in each bucket is some left-leaning red-black tree, which we, I don't know, I'll just draw one so that we have a good idea of what's going on. Remember what's special about a left-leaning red-black tree. It's basically a 2-3 tree. So it's self-balancing. It's a self-balancing binary search tree, and therefore it's always going to be bushy. And so when we're looking for stuff or adding things to a LLRB, we're always going to have logarithmic runtime. And that is going to factor into this question a lot. So part 1 says the runtime of contains on this hash table is big O of n. And so here, let's actually just try and think about, okay, what is the runtime of contains going to be on this hash table? And so when we call contains on some element, what we'll end up doing is we will calculate its hash code. Let me move this over so you can see hash code, and then we will mod by M. So we'll go to this bucket. So we'll have to go to that bucket. And that like whole process is constant time. And once we're at that bucket, we have to search the LLRB at that bucket for X. Okay, and so if we think about what we know about LLRBs, if there are, I don't know, let's say C elements in a LLRB, contains in that LLRB is log of C, because it's a balanced binary search tree. And so if we have n elements in our hash table, we want to think about, okay, how many elements can there be in any one of these LLRBs? It doesn't tell us to assume anything about the hash code, right? The hash code could be terrible and always go to bucket 0. And so in that case, right, we'd have n elements in our LLRB that we're going to call contains on. And so in that case, right, the runtime of contains will be log n. And there are lots of other cases, right, when there are less than n elements in that LLRB. There could be just like 1, so then it would be quite fast. But we have figured out what the runtime of contains is. And now we can answer these questions. The first question says, true or false, the runtime of contains is big O of n. And that's true, right? Because we figured out, we said this runtime of contains, we're going to go back to here, is big O of log n. So log n is big O of n, right? This says the runtime of contains is big O of log n, and that's what we just said, right? So that's true. And then this says the runtime of contains is big O of 1. And remember, big O is less than or equal to, and so this is false because log n is bigger than 1. Okay, question 4 says iterating over all of the keys in the set in ascending order takes linear time in the worst case. So the question is like, do we have the keys in sorted order? Like, can we just like pass through the hash table and get our keys in sorted order? And kind of the insight here is that the hash code doesn't have to respect the ordering. Like we could have some element in this bucket, some element in the 0th bucket, and then some other element in this bucket. And it could definitely happen that the element in the later bucket could be smaller than the element in the first bucket, or it could be bigger. Like we don't know anything about these orderings. So don't know anything. Even though we have these items implementing comparable, and within the LLRB, they're in like a semi-sorted order. The buckets that these LLRBs are in aren't necessarily sorted at all. So don't know anything about these orderings. So the answer to this question is false, because we're not going to be able to iterate through all the keys in ascending or in some sorted order in linear time. It's going to take longer than that. We're going to have to like pull them all out and then like run a sorting algorithm on them or something. And question 5, this is from the HashMap lab. Actually, we did like an experiment with this. It says, assuming that items are nicely spread out in the hash table, we expect that an LLRB bucket would yield significantly better performance for contains and add than if we used an array list for each bucket. And so basically we're saying, okay, if we replace, we said, okay, no, we don't want to do an LLRB anymore, and we have an array list here, does that like make our hash set or this hash table slower doing contains and add? Or kind of the opposite is using an LLRB much faster. And the key point here is that we're assuming that the items are nicely spread out in the hash table. And so we talked about in lecture how from this assumption, and if we're resizing, we can just assume that we have a constant amount of elements in each bucket. And the key here is then it's going to be constant time for contains and add, no matter what data structure we use in our bucket. Fine, maybe like the LLRB will be log of a constant, but in our like asymptotic analysis, we just drop constants. So anything constant is like theta 1 runtime asymptotically. So the answer to this is false. Let's move on to part B. Part B says, suppose now that we build a set of picture objects using a hash table, and we're doing linked lists in the buckets. And this is a kind of diagram that shows us what our set looks like at some moment in time. And it gives us the hash codes in red next to the picture objects. So one says we're going to add a new picture with hash code -6. In which bucket will this new picture end up in? We're going to assume that the hash table doesn't resize, so we don't need to like double the size or anything before we add. And we're going to assume that we handle negative hash codes as described in lecture. And so what we have to do, right, whenever we add something to a hash table, we hash it, we get its hash code. And so we have -6, and then we'll mod by the number of buckets. So the number of buckets, or like how long our underlying array is. And in that array, we're storing these data structures that actually contain our items. So in our example, we see that we have 5 buckets, 1, 2, 3, 4, 5. And so we want to calculate -6 mod 5. And this is the math mod. Let me move this forward again, the math mod. Not like Java mod, because we know that Java does weird stuff with mod with negative numbers. If you didn't know to try that out, try doing like -1 mod 5. And in math, -6 mod 5 is going to be equal to 4. And the way that I do this is usually like with smaller numbers like this, I'll add and subtract 5 until I get in the range that I want to be in. Because like adding and subtracting 5 is basically like doing nothing, because 5 mod 5 is 0. And so what I do here is say -6, okay, add 5 once and we get -1. And then if we get -1, we add 5 again, we'll get 4. And so 4 is in the range that we're interested in. And so -6 mod 5 is going to be 4. So we're going to put this new picture in bucket 4. Okay, more hash codes. Question 2 says, if we resize our hash table by doubling its size, items with which hash code will end up in different bucket numbers, in a different bucket number than before the resize operation, sorry. Assume we're starting from the original figure above without the alien. And so all we have to do here is think about, okay, I'm going to have a new hash table, and it's going to have double the amount of buckets, right? So we'll have 0, 1, so on and so forth. And the last one will be index 9, because we're going to have 10 total buckets. And so what we have to think about here is for each of these hash codes, which ones, when I mod by 10, am I going to get a different result? And so we can start with 5. If I say, what is 5 mod 10? 5 mod 10 is just 5. And so in our new hash table, we're actually going to put this picture at bucket 5 rather than at bucket 0. And so that will be one that we check. Okay, 1, we're going to say, okay, what is 1 mod 10? That just gives us 1. And so we're going to put it in bucket 1, and that doesn't move. 3 is the same thing. 3 mod 10 is 3, and so it'll stay. 103, right? 103 mod 10 is also 3. Because, I don't know, 10 divides 100, and there's 3 left over. So we're not going to check 1, 3, or 103. But we will check 28 and 9, because when we say 28 mod 10, we'll get 8. And then we'll put this, this picture object in bucket 8, but right now it's in bucket 3. So we'll check 28, same thing. 9 mod 10 is 9. And so this blue guy is going to go in bucket 9, which isn't the same as bucket 4. Finally, part 3 says, suppose that we perform the following actions on the original hash table with 5 buckets illustrated in the image above. We're going to add this blue guy, which is the same as here. It's going to have hash code 9, and so it's going to go in bucket 4. We are going to call this turn pink method, and then we're going to print out hash table.contains x. We're going to assume that the turn pink method changes some of x's pixels pink and adds a third eye so that it looks like, I don't know, this pink picture. This change to the object may result in its hash code changing. The question says, for which of the following hash codes will line 4 of the above code print out true? Note that a picture objects equals method returns true only if their pixel values are exactly identical. And so the heavy lifting here is basically, we have inserted this object, and now we're going to change its hash code. And when we try and see if our hash table contains the changed object, we have to go through the process, right? We'll hash x, and we're going to go look at that bucket for x. And so I can actually draw it out. So this is bucket 4, and we have our blue guy with hash code 9. And then what we do is we change it to be pink, and this hash code changes to something. And what we do now is we're going to say, okay, do we have pink? Under what circumstances? And so what we're going to have to do is we say, okay, what is pink dot hash code? I'm calling it pink. This is just like the pink version of x. This is still x that sits here. So I can actually, to make this less confusing, say it contains x. And we're going to do x.hashcode. And we have to mod by 5 because we have 5 buckets. And so we're wondering, okay, what values for this hash code are going to let us say that we have x. And you'll notice that this only will work when we say that x.hashcode mod 5 is 4. In all other cases, right, we'll call contains, we'll do this hash code thing, we'll mod by 5, and then we'll go to that index. And let's say we go to index 0. X is definitely not going to be in whatever data structure. I think in this example, we're using a linked list. X is not going to be in the linked list at index 0. X is in the linked list at index 4. And so we basically just need x.hashcode mod 5 to be equal to 4. And the values for which that'll happen are -1, 4, and 14. For 0, we'll go to bucket 0, and that doesn't work. But -1, 4, and 14 mod 5 are all equal to 4. And so the equals method, this line will print out true under these circumstances. Thanks for watching.